Okay, I think we can start. So hi everyone. So today we have the pleasure of having Joris Boss for the last seminar of this year before the summer break. So let me introduce Joris. So he obtained his PhD in astronomy and astrophysics at the University of Leuven in Belgium in 2015. Then he did a 3-year postdoc as a Fondesit, I don't know how to say this, fellow at the University of Valparaiso in Chile. And now he's currently a Humboldt Fellow at the University of Potsdam in Germany. So he's working mostly on hot subdwarf binaries, as we will see here, both on the observational and theoretical side. And he's been also recently adapting the stellar evolution code MESA to test improved interaction models. So you can start. And before you start, I would like everyone to mute themselves and also remove their video so that we can have a nice streaming during the talk. So you can go ahead.
Okay, thanks for allowing me to give a seminar here. So yeah, as already mentioned, I work on hot subdwarf binaries, and what I want to do with them specifically is to study binary interaction mechanisms. And obviously, I don't do that alone. So the work that I will present here today was done in collaboration with Alexei Bobrik from Lund University, who is present, and with Maja Vukovic from the University of Valparaiso. So, well, let's start at the beginning. Why would we be interested in studying binary interactions? And well, the answer is actually not that complicated for this. A lot of binaries will at some point in their life undergo interaction phase. So if we look at low mass binaries, less than 2.5 solar masses, about 30% of those will at some point interact. And this gives rise to some very interesting systems like supernova 1a, blue stragglers, algos, cataclysmic variables, and of course also the hot subdwarf binaries that I work on. So what I focus on specifically is the interaction on the red giant branch, because that's what will produce hot subdwarf binaries. We do understand in big lines what happens during these interactions, but there are still a lot of details that are not very well understood. And that is a bit the background on why we want to work on this. So if we want to study a binary population, then there are basically 3 main ingredients that you need. So the first is that you need a test population that you can use to test your models. And in our case, that will then be hot subdwarf binaries. Second thing that you need is your binary interaction model. And the third thing is your initial population that you want to run through your interaction model and then compare to your test population. And that is where, as you will see, galactic evolution will come into play. So let's start with the beginning here, the hot subdwarfs. So what exactly is a hot subdwarf B-type star? So as the name says, it's subdwarf B. So it looks like a B-type star, but with a much higher surface gravity, which can be seen in the fact that the lines are much broader. In the HR diagram, they are located at the extreme blue end of the horizontal branch. So this indicates that they are core helium burning stars, and because they are really at the very far blue end, this would indicate that they have lost the majority of their hydrogen envelope somewhere before this phase. So they are evolved low mass stars, typically less than 2 solar masses, that have ignited then helium degenerately. we can look at an evolutionary track of such a system. So you start out with the low mass star, for example, a solar mass star. It will ascend on the red giant branch, and then near the tip of the RGB, before the core is massive enough to ignite helium, you get an interaction phase, and this can be stable Rorschach overflow or maybe a common envelope phase that removes the entire envelope or almost the entire envelope. So you only have like a few percent maximum left. And then you ignite helium in the core, which is happens degenerately. That is what these flash thingies here are. And then it starts burning helium in the core stably, and that is where we actually observe them. So the stable core helium burning phase takes about 100 mega years. And when that phase ends, you can have a phase of helium shell burning. But after that, that's it. So these stars are not heavy enough to ignite anything else, and they just end up on the white dwarf cooling track. So these wiggles here are the helium ignition. So helium ignition happens off-center due to neutrino cooling, and then consecutive flashes will flash closer and closer to the center until you eventually ignite the core. So how can you make a star like this? Currently, it is pretty much agreed upon that the only way to make a hot subdwarf star is in a binary system through some kind of interaction phase. And there are three main evolution channels. So we have stable Rorschach overflow, where you start with a main sequence plus main sequence binary. The primary will ascend the RGB, will start Rorschach overflow. This remains stable, so it loses its entire envelope, and you end up with a SDB plus main sequence star on a long orbital period, on the order of a few years. If, however, your interaction phase would be unstable, you can get a common envelope, and then if you manage to eject the common envelope, you can also end up with an SDB with the main sequence companion. Or if this would happen at a later stage in the evolution, you can have an SDB with a white dwarf companion. And these systems then have orbital periods on the order of hours to days, and I think the longest one is at around 30 days. And the third way of making a hot subdwarf star is in a merger. So if you have two helium white dwarfs, they can merge and form a single SDB. The systems that we study and that I will talk about today are these ones. So they're the ones that are formed through stable Rorschach overflow. It consists of an SDB with an FG or K-type companion. This has as an advantage that you can see both the SDB and the main sequence star in the spectra, so double-lined, and this gives you information of both systems. It seems that all of these are from a single simple population. So they have only undergone one interaction phase, because the companion is still just a main sequence star. And the mass distribution corresponds with what is theoretically predicted. So it seems to indicate that indeed all of these systems are formed in the same way. And that is very useful because that means that every new system that you can solve will give you an extra data point for your theoretical models. So we have been observing these systems for quite a long time now. We started in 2009 with the Mercator spectrograph at the Hermes spectrograph at the Mercator telescope here in La Palma. And then later on, this observing program was extended to some southern telescopes, of which the main that we used is UV spectrograph at the VLT. So we have been following 34 targets, of which we have now about 24 with fully solved orbits by now. So let's have a look at what are the most interesting things that we have found in these orbital properties of these systems. So the first thing that we noticed well, is the orbital periods. So all of these systems have orbits that are in excess of a year, and they go up to, well, 3, 4, 5 years long. This was not predicted. So in the theoretical work from Zhang and Han from early 2000, that is, the stable rush slope overflow SDBs were predicted to have orbital periods around roughly 100 days. However, we don't see any observations, any systems that have periods around 100 days. They're all way shorter or way longer. It turns out that this is most likely related to a misclassification. They used single star models in a binary code, and this might have led to classifying helium white dwarf as SDBs. And this was later on fixed by Shufai Shen, who has redone those studies. And they actually find that when they use their models, which include atmospheric rush overflow, that the orbital periods that they predict match very, very well with the orbital period distribution that we have observed. Now, you might have noticed that there is another interesting point in this figure, and that is that, well, most of these systems are eccentric. So as you can see, there are only 2 systems shown here that have circular orbits. And this is not expected. So if you have a binary with an orbital period of a few hundred days, and your primary becomes a red giant and eventually will fill its entire rush slope, all tidal interaction theories will predict these systems to completely circularize long before the interaction phase even starts. So in theory, all of these systems should be circular. However, in practice, they're not. So this seems to indicate that there might be some kind of eccentricity pumping ongoing during the interaction phase. And this is something that is actually visible in other types of stars too. So this is not only for the hot subdwarf binaries, but for example, in post-AGB stars or barium and S-type stars, which are also are post-interaction systems. As you can see on the graph, a lot of those are eccentric. And once you pass a certain orbital period, like around 3,000 days, you don't even find circular ones anymore. And more recently, we also found that this was found in delta Scuti binaries as well. I will get back to this period eccentricity thing a bit later in the talk. But what we will talk about most is this relation. So the period mass ratio relation that we have observed in our hot subdwarf binaries. So as you can see, there are 2 groups visible here. So we have a main group with the most systems in blue, which has a very strong PQ relation of basically, if you assume that the SDBs all have the same mass, which they kind of do, shows that the K-type companions can be found at the shorter orbital periods, and the SDBs with then the heavier F-type companions will be found at longer orbital periods. And then there are 4 systems in a second group, which seem to follow the same correlation, although of course with just 4 systems, this could be chance. And this is the relation that we will try to explain in this talk. So that is our test populations or hot subdwarfs. Then we get to the binary interaction model that we will use. So if we look at binary interaction, just by looking at the mass loss rate, you can kind of distinguish 3 different mass loss phases. So when you start out, your red giant slowly starts to fill its rush slope. You have a very low mass loss rate, less than about 10 to the minus 5 solar masses per year. This mass will go through the inner Lagrange point, end up around the companion, and the companion can still accrete all of this. So this is most likely conservative mass transfer, and it has you still have very slow evolution. Then when your red giant increases further in radius, so it starts to overfill its rush slope, you get much stronger mass loss, and at that point your companion cannot keep up anymore. So the mass still mostly goes through the inner Lagrange point, but it gets lost from around the accretor. And then if you would continue even further, so if you go to more than 10 to the minus 2 solar mass per year, you will get into a phase where the donor star will start to overfill its rush slope so much that you start to lose mass through the L3 point, which then the outer Lagrange point, which is the point behind the donor star. It turns out that most of our SDBs that we form in our models will never get to this third phase. And I think many people actually assume that once you get to that phase, you get unstable mass loss and you start a CE phase. So let's have a look at how this is then implemented in MESA. So this is the very first model that we used. And this is also what is mostly implemented in MESA at the moment, apart from the disk part of this figure. So you have a mass loss range, which is determined by Kolb-Ritter formalism. You assume some kind of stability criterion, can be based on the rush slope overflow factor, or for example, the mass loss rate. And then you define what happens with the mass. So it can be accreted by the companion, or it can be lost from around the donor, from around the accretor, or through the outer Lagrange point. And that is then defined by the mass loss fractions. For example, the ones from Taurus and van der Heuvel, which are implemented in MESA. This was the model that we actually used to study the eccentricities, or test several eccentricity pumping mechanisms. So this also includes parameters for a circumbinary disk. And as you can see, this model has a lot of free parameters, which we cannot, most of which are actually not constrained at all. This is a problem, and I will show why. So we tested several eccentricity pumping mechanisms with this. And basically the two that seem to work quite well is a phase-dependent mass loss, where if you lose mass, more mass from near abastron than near periastron, you can increase the eccentricity. And if you form a circumbinary disk, that disk can, if it is stable, interact with the binary and also include the eccentricity. So if you then adjust all those parameters in that model, it is fairly easy to cover almost all observations. When we did this work, this second group here wasn't known yet. That's why the models don't cover it, but it's fairly easy to further change the parameters to include this as well. And that shows immediately what the main problem of this type of model is. It does not have any predictive power. If you cannot, you can use it to show that a model that you are trying out can indeed explain a certain phenomenon, but you cannot predict what will happen to a certain system with this. So we want to do better. And what we came up with is actually a slightly simpler model. So we use a interaction model that is fairly basic, but is well accepted in the literature. So we again have the mass loss range, which is determined by Kolb-Ritter. The difference here is that we have extended that so that you can calculate analytically how much mass is lost through the inner Lagrange point and how much mass is lost through the outer Lagrange point. So you don't have any need for these mass loss fractions anymore. And then the model basically, all mass that goes through the inner Lagrange point will end up on an accretion disk around the companion. The companion will accrete mass from the disk until it reaches critical rotational velocity. and any further mass that is lost through the inner Lagrange point will be lost from the system with the angular momentum of the companion. And if there would be mass loss through the outer Lagrange point, so if your donor star is really overflowing a lot, then it will take the angular momentum of the outer Lagrange point, the L3 point. Since we've only looked at circular orbits, we don't have any need for a certain binary disk and so on. So this model has no adjustable parameters anymore. So that means that if you define the initial state of your system, like the primary mass, mass ratio, initial orbital period, and metallicity, you have defined the entire outcome of the system as well. So since we now have our binary interaction model, we need to find an initial population to feed into this model and then compare with our observed population. And this is where we get into the galactic evolution thing, part of the talk. And that is also, I think, the part that is new, or that might be new for most of you. So galactic evolution, or galactic models, basically, what would it mean is, or what they are, is you try to make a model that explains the galaxy how we see it. And you can basically do this by looking at low mass stars, because if you have a low mass star, they have lived for quite a long time. And that means that they will act as a time capsule for the state of the galaxy at the time that they were formed. So you know how the galaxy looked a long time ago. And then typically a galaxy model has 4 different components. So you have the thin disk, which is the stellar and gaseous disk, which is also the only part that really has ongoing star formation. And you have the thick disk, which is formed as a dispersed population of the thin disk. You have the halo, which is a very old population. And then you, of course, have the bulge, which is also a very old population, but due to self-enrichment has a much higher metallicity than, for example, the halo. And what is now actually the reason to look at this? And that's the metallicity. So we want to know how the metallicity depends on the initial population that we use, because the higher the metallicity of the system, the higher the opacity, the stronger the convection during the RGB phase, which leads to larger radii on the RGB. And of course, if you get stars that get larger on the RGB, this will affect what type of binary interaction you're going to have. And that is why we are interested in getting this correct. So we have used the Besancon model, and the Besancon model is, so the Besancon model aims to explain the currently observed galaxy in the solar neighborhood, and it's calibrated by large photometric studies. So it subdivides the galaxy in 10 different bins, and each bin then belongs to one of the 4 populations, 7 bins in the disk, 1 in the thick disk, halo, and bulge. And then each bin has a certain age range, a certain metallicity range, it has a certain amount of mass, and it has a star formation rate. And then we draw stars from these bins to have a starting population for our population synthesis study. Now, you might wonder what this actually means for us. So we can have a look at FGK type stars in the solar neighborhood. So this is a sample from Bensby et al. And here you plot the metallicity versus the age of the systems. And I mean, this plot looks very logical. So if you have systems that are young, they formed recently, they will have a much higher metallicity, so around solar or even higher, than a star that has formed like 10 or 12 giga years ago, which will have a much lower metallicity. So the metallicity of these systems depends on their age. And this is something that is typically ignored in BPS studies. You typically use a few distinct metallicities, or you assume a uniform metallicity distribution. Now we can do this slightly differently, or we can look at this slightly differently, because we are working with systems that have to evolve off the main sequence. So that means that if you look at a star spends most of its time on the main sequence, so everything that happens afterwards is very short in comparison. And for these stars, low mass stars, the time that they spend on the main sequence is very strongly linked to the lifetime. So the mass is very strongly linked to the lifetime on the main sequence. So this allows us to say that if we want them to evolve off the main sequence, then we can link their mass directly to the age of the system. And because the age of the system is linked directly to the metallicity, what we will find is that the mass of our systems is, or the metallicity that the system can have, depends on the mass that the system can have. And that is shown in this graph here. So if you have a higher mass, like for example, a 2 solar mass star, this star has evolved off the main sequence, but it has formed fairly recently. So it will have a metallicity that is around solar. If you compare that with a 0.7 solar mass star, which, if it is now evolved off the main sequence, must have formed a very long time ago, and will actually have a metallicity that is much, much lower, like around -1 or lower. And that is that relation will turn out to be quite important. And that's what we then have used in our models. So we combine this with then also, of course, a mass distribution, Krupa and Highwood, a mass ratio distribution, which is flat, and a orbital period distribution, which is the log normal distribution. This is all very typical for population synthesis studies. And from this, we then pick 2,000 systems that we run through MESA, and we find that about 15% of those form SDBs. And then there's, of course, one more step, and that is to link the models to what can be observed. So we need to select that they are indeed looking like an SDB spectroscopically. They need to be composite binaries, so you can't have like dwarf or giant companions, because we would not have selected them in our observations. And we have only systems from the disk or the halo. We have no observations in the bulge. This approach is new. So as far as we could find in the literature, there were 3 articles that use this, that actually use a galaxy model in their studies, but ours is the first one that actually also compares it directly to an observed population. So we have our 3 components now. So we have our test population, we have our model, and we have our initial population. So let's see what comes out of that. So as a reminder, this is the graph that we want to explain. We want to understand why there is such a strong correlation between the observed mass ratio and between the orbital period. So we can now run our different initial population through our model. So we can start with the very simple one. So that has a constant metallicity or a fixed metallicity and a constant star formation rate. And here you can see that this obviously cannot cover all observations, so this doesn't work. Then other typical approach is the uniform metallicity distribution. So on the left here, you can see what that means. The mass is not correlated at all to the metallicity. It's just random. And you see that indeed, these models can cover all of the observations, but it does not reproduce the correlation that we see. So it's a better model, but it's not what we want. And if we then use the actual galactic Besancon model, so where you here have this nice relation between the donor progenitor mass and the metallicity, you can see that these models match very well with the observations. at least with the main branch of the observations. So the second population of those other 4 stars, we still don't really know what is happening with those. Now, where exactly does this correlation then originate? So we can show that with this plot. Now, this is a very dense plot. There is a lot of stuff on this figure, but I will simplify it as far as I can. So what it shows is we have taken 3 models, so a 1 solar mass, a 1.2, and a 1.8 solar mass, taken initial parameters that make an SDB out of these models, and then for each of them varied the potential initial parameters. So we varied the metallicity, the initial orbital period, and the initial mass ratio. So the 2 parameters that turn out to be important here for this PQ relation are the metallicity and the initial donor mass. So the metallicity, as you see here, the metallicity only changes the final orbital period. And we already know why that is. It has no influence whatsoever on the final mass ratio of the system. The final mass ratio is actually determined by the initial mass of the system. So there is only a small range in initial mass ratio that will allow you to create an SDB. If you go outside of that range, your mass loss will be too strong, or the mass loss phase will be too fast, and you will end up with a helium white dwarf, or it will be too slow, and you will end up with a horizontal branch star, which will eventually go up on the AGB. So only a small range can actually make an SDB star. And then because the final mass of the SDB is not really dependent on the initial mass, it's always roughly the same. And because the companion doesn't really accrete mass, very little actually, only a few % of a solar mass at most, this initial donor mass then pretty much determines where what the final mass ratio is going to be. So if you combine the two, the initial donor mass determines what the metallicity range is that it can have due to galactic evolution, and determines what the mass ratio is that it can have. So by combining these two, you get this nice relation of higher initial donors, which have a higher metallicity and thus a longer orbital period, and at the same time will end up on lower mass ratios, and for the lower donor masses, it's then the opposite, and this gives this nice correlation. So there are more things that we can check with this model. So we can look at other galactic populations. So this was mainly the thin disk, where most of our systems are from. But we can also look at how other populations would look. So for example, the bulge, which is an older but a metal-rich population, this would look quite different in the PQ diagram, or the halo, which is just a small, which would only cover a very small part. So this could be a test for the model, where we can focus on systems that come from the halo, or potentially from the bulge, although the bulge will be quite hard to observe. And then the second thing, of course, is the relation between the orbital period and the metallicity. So this is actually, this relation has been suggested in the past for SDBs by Shufai Shen, for example, or for helium white dwarfs by Alena Istrate. But they have never been fitted to observations. And we can now actually do that. So I talked a lot about the metallicity already, so let's see if this actually is correct. So for now, we only have 12 SDB binaries for which we know the metallicity. So the metallicity is determined by analyzing the spectrum of the main sequence companion star. So it should show the metallicity at the beginning of when the system was formed. And as you can see, there is a very good fit between the observed metallicities of these systems and their observed orbital periods with the models that we have calculated. So from this, we can conclude that indeed, if we take this analytical model for binary interaction on the red giant branch that we've used, and we combine this with an input population that is consistent with the galactic evolution model, we can reproduce our PQ relation in wide SDBs very well. So where do we go from here? I want to briefly advertise a Python package that we wrote to make this kind of studies a bit easier. So NAPS is a Python package that aims to simplify using a 1D stellar evolution code as a population synthesis code. So it's meant to be used together with MESA, although you could probably change it quite easily to use other input models. So it allows you to easily extract parameters that are of interest from a large grid of models. You can apply CE formalisms, and if you really want, you can even use it to then afterwards calculate mergers with MESA again. And it also allows you to train a neural network or another type of predictive model so that you can use the models you have calculated with your 1D code as a population synthesis code. We have basic documentation available already, and we're currently writing a bit more detailed documentation, and the link is mentioned here. So just to show that it is indeed making things easier and not more complicated. So NAPS allows you to just, you can set up a whole grid of MESA models, and then you can tell it what you really want to keep. You can define a couple of like the CE formalism and stability criterion, and then you can very easily say, what parameters are you interested in? So for example, if you're interested in the core mass during helium ignition, you can define that very easily, and NUPS will calculate that for you for each model where there is actually helium ignition. Or you can do observables. You can have the effective temperature during the helium core burning phase, and it will then take the average over that phase. It can automatically recognize several evolutionary phases. And that will then afterwards give you a nice 2D table containing one row per model and one column per parameter that you're interested in. This you can load into a predictor. So with only a couple lines of code, you can set up a neural network or another type of model, fit it to your data file. So for example, here, say we want to use as input parameters donor mass, initial period, initial mass ratio, and not written here, but also probably initial metallicity. We want to get out the final orbital period and the final mass ratio. It will fit that, and then you can give it like a whole model, like based on the Besancon model, for example, and then it will turn that plot that I showed earlier into a plot that contains about 1 million models, like what you typically get in BPS studies. So we are currently using this, and we're trying, focused on two other problems in binary interaction. So the first one is, when exactly becomes your mass loss phase unstable? So for this, we're comparing the post-CE SDB binaries with the ones from stable rush slope overflow. And we're looking at the companion masses, because it turns out that if you change your stability criterion, you can you get a very big change in the mass distribution of your companion masses. So by comparing the predicted distributions here with the observed distribution, we hope that we can get a better idea of where exactly your mass loss becomes unstable. And the second thing that we're looking at is the actual angular momentum loss during rush slope overflow, because it turns out that if you change the angular momentum loss, you don't really change the final orbital period of SDBs, because you will just need different initial orbital periods to make SDBs, the one. But because, of course, your initial orbital periods are limited to a certain range, at some point you will not make SDPs anymore. So by looking at the distribution in final, we hope that we can limit what during Rush-Lob overflow. So with that, I conclude. We have now 24 solved white-hot subdwarf binaries based on 11 years of observing, of which we have found a few very interesting correlations in their orbital periods. These are very useful objects to study binary interaction mechanisms, at least in my opinion. And we have used them indeed to test a binary interaction mechanism that is widely supported in the literature. And we have found that indeed, if you use this analytical model for binary interaction on the RGB, and you combine this with a correct initial population based on galaxy evolution, we can very well reproduce the observations of our white SDB binaries. So this shows that if you have stars, or if you're studying stars that are evolved, so that have moved off the main sequence, and they are low mass stars, like less than 1.5 solar mass, it is important to take galaxy evolution into account when you're studying them. Thank you.
Well, thanks a lot, Joris. Very interesting talk. I guess everyone is uploading on their virtual screen. Okay, so now maybe you can go ahead for the questions. I don't know if anyone has a question. You can unmute yourself and ask your question to Joris. Well, in the meantime, maybe I can start. Mm-hmm. So you were talking about this eccentricity pumping. I'm not very aware of this. Can you say how that would happen exactly?
It is in both cases that we studied, you do need a slight initial eccentricity for it to work. But if you have a binary orbit that is slightly eccentric, this will cause you to lose more mass near apastron when the stars are closer together than near periastron when they're further away. And this difference in mass loss during the orbit will cause your orbit to become more eccentric. It's a small effect, but if it can last long enough, it can actually significantly increase the eccentricity of the system. And then the second way is that if you make a circumbinary disk, you do need a stable disk for this to work. It can interact with the binary through Lindblad resonances. This has apparently been observed in, how are they called? I think protoplanetary disks, sorry. So the disk can indeed also slightly increase the eccentricity of a system. And this could potentially explain why we observe eccentric systems that are post an interaction phase.
Okay, but for the moment, you're not taking this into account in the models?
No, in the latest models, we haven't included eccentricity yet. That is something that we still wish to do, but haven't gotten around to yet.
Yeah, I was wondering if that could explain why some of the systems you're seeing, especially the ones that you can't reproduce, the mass ratio, the lower, the orange points. Yeah, no, that wouldn't explain
anything. We don't think so, because
no.
they show a similar eccentricity distribution than the main systems. So it's probably not related to that.
Okay. Okay, so any questions from the participants here? Okay, it doesn't seem so. So I have another question then.
Okay.
I think I remember there are some SDBs that were observed with K2 and now with TESS.
Yes.
I'm not sure if these are in binary systems or they are all of them.
I think there is one that is in a long period binary, but we don't have an orbit for the long period system yet. So we just see that there is indeed a low radial velocity variation that could indicate like a period of a couple of years.
So, but are you planning to try to get more in?
We are following that system at the moment, but it will probably take a while before we solve it.
Okay. Okay, so it seems no one has any other questions. No.
Okay.
So thanks again for your talk. I will also try to have a look at your MESA implementation of the the artificial intelligence thing is going so widely that it's very useful and interesting to apply to other systems. So
yes,
I'm interested in that. So.
Oh, okay. Then you should certainly have a look.
Yeah.
Great.
But thank you again then for giving this talk.
Yes, thanks.
And thanks everyone for joining in. And so as I said, this is the last seminar of this month, and next month we won't have any seminars and we will start again in September. Not yet sure if it will be Zoom seminars or we will get back to the normal face-to-face. Maybe we'll do a mix, I don't know, but anyway, we'll keep you posted. And so yeah, everyone take care and see you next time. Okay, bye.